Yes, ma'am.
Yes. Okay, cool. So Ujjwal Patel. Okay. Uh, Ujjwal, is it Ujjwala? Okay, it's left the. Okay, fine. So anyway, yeah, you all have to join in with your IIT Goa address only. So if any of your friends are trying to join, please let them know that. Okay. So let's get started. Yesterday we were looking at the A star optimality, and there was some issues that I told you of. I mean, it's just something to be aware. I thought like anyway this issue is there, but let me just anyway tell you guys because in a class it's about also this. It's not just about telling you a bunch of facts, right? You see how things are analyzed and what possible issues are there, and these kind of things are also part of your overall development, right? So that's why I thought I'll anyway do that proof. Yeah, I don't know if that was resolved, but I think we'll come back to it later if somebody has found a solution to that. The thing was, with consistency, the proof of A star being optimal, right? In a graph search scheme. So that's something, but I think the statement is true anyway. So let's take it by faith. And so what we were doing towards the end of the class yesterday was about the design of heuristics. Right? So we talked of admissible heuristics, we talked of consistent heuristics, and I was just showing you this example of this 8 puzzle problem where there are multiple heuristics. Typically that's the case, right? For every problem, like it's possible to come up with different heuristics. So given this, what is the heuristic, which one should we choose, right? So that's where we talked of this 8 puzzle problem. So one possibility, so here the problem is that you have all these numbers and there's one blank tile. So you want to get to this state on the right side, so where all the numbers are contiguous and the blank is on the top leftmost corner. Okay, so one possible heuristic is like how far are you, like how many tiles are misplaced, right? So it should give you some sense of the cost of getting to the goal state, right? So the possibility is one option is to go with number of tiles which are misplaced. So yeah, it's admissible, so you have to convince yourself about why it's admissible. So think of that. And yeah, another possibility that was there was this notion of Manhattan distance. So as per the rules of the game, you cannot move diagonally. So you cannot move the 8 to the middle, to the blank. Okay, you can only move, maybe 5 to, so you can only have like left or right movements or top down movements. Okay, so that's why the Manhattan distance. So for each tile, you see how far it is, what's the distance from its current position to where it is supposed to be actually. So if you take one, for instance, in the start state here, the one is at the at the left. I mean, sorry, at the right, bottom right position, and it has to, if it has to come up to its actual position in the goal, it has to move one position to the left and 3 positions up. So it has to move first to the left and 3 up, or go up and then left, whatever. But overall, there'll be like 4 moves it has to do, or 3, right? So 1, 2, 3. So total 3 moves. Okay, so that is for 1. Now the 2 has to at least move once to the right. Okay, so that is 1 move. Okay, so actually you might end up doing more, but this is the bare minimum that has to be done. So that is another possible heuristic you could take, the Manhattan distance. So here there is a comparison that's there, like if the optimal path had just 4 moves and you used the first heuristic, which is the number of tiles misplaced, then how many nodes would you expand? And whereas if you used the Manhattan distance, how much would you expand? Okay, so as you go larger and larger, suppose the start state is very bad and so that the optimal path has 12 steps, then here the last column in this table gives how these two heuristics perform. And here you can clearly see that the Manhattan heuristic explores much less. Okay, so both are admissible heuristics, but the Manhattan distance explores much less. Okay, so it's faster. So how do we know this? Like, how can we see this beforehand? Or is there really some way to know it before? Okay, so this brings me to this notion of some of the family of heuristics. So just a second. Yeah. So as I said, that you can have multiple heuristics. So we'll just focus on admissible heuristics for now, because one point I mentioned was this tree search. If you do a tree search instead of a graph search, admissible heuristic is sufficient to guarantee optimality. So let's you could do something similar for even with consistent heuristics, but let's just because admissible is a little easier to construct relations between heuristics, we will just look at the family of admissible heuristics. So let me just write this. So okay, so family of admissible heuristics. So remember that admissible heuristic was one where the heuristic satisfied this relation. H of n was less than h of n star. Sorry, h star of n. H star of n for every state n. Right? This was what we defined as an admissible heuristic. So the heuristic is in some sense actually optimal. So now, suppose you have two heuristics, right? So suppose you have HA is one heuristic, and maybe you have another heuristic HC. So both are admissible. So let's say both are admissible. Now, one thing we can do is we can also, in some cases, we can also define a relation between heuristics. For example, we can say that, this is something that I'm defining now. So this greater than or equal to notion for these two functions. So what does this mean? So we say that HA has a greater than equal to relationship with HC if, for every state you take, so HA of n should be greater than HC of n for every state. So every state you take, HA, the value of HA dominates HC. Okay, so that's what we mean by this greater than or equal to relationship. So it needn't be like you can have like heuristics which don't satisfy this relation. For example, like for one state you can have one heuristic is better, is larger, whereas for another state you can have HC is better, something like that. That can also happen, but you can. So there are instances of heuristics which are comparable in this manner. Okay, so let's look at some examples. So one example heuristic is just the zero, right? So the zero heuristic, so h0, it is h0 of n equal to 0 for every state, right? So for every state n, the zero heuristic. So then what happens when you use A star algorithm? Remember, you're using g of n plus h of n as the heuristic, and h of n is 0 for every state, right? So then what do you get back if you use h0?
Uniform search.
Uniform cost search, right? Yeah. So if you use h0, you will get the uniform cost search. Okay, and this is anyway optimal. So optimality is not going to break down, but you might have a lot of exploration. Now, maybe there is some other heuristic like this, say HA. Okay, and so HA is something like, you have like greater than 0 values always. So, there's this relation. So I'm marking an edge between HA and H0 if, HA is greater than or equal to H0. Okay, so I'm just trying to form a graph out of this. And maybe there is some other heuristic here, say HB. Okay, so HB is also an admissible heuristic, say, and it's greater than H naught. Okay, now maybe HA and HB are not comparable. that's possible, right? And maybe you have something here, say HC, where HC is strictly dominates HA. Okay, so for just for the sake of consistency, let me make this H like reverse case, because the definitions I've just written it this way so that you don't get confused. So something like this. Okay, so HC comes here and HA is there. Now another operation that you can do which preserves this admissibility is if you take the max operation. So if you take max of HA and HB, for instance. Okay. So what this is telling you is, for each state, you take the maximum value. So it is max of, HA of n and HB of n for each state, for every n. Okay, so for some states, HA will dominate, it will give you a larger value. For some other states, HB will dominate, it will give a bigger value. So this is also going to be admissible, right? Because HA and HB, both of them are admissible. So if in that case, the max is also going to be admissible because it's just one of them. So you can have this kind of a relation between them. Is a max, HA, HB, and so on. So there are many possibilities. And at the top of this, you have exactly the value of H star, right? Because all of these are, they are dominated by H star. Okay, because they're all admissible heuristics. Now, if you have H star, so this is the exact distance, right, of each node from the goal. Okay, so this is something we discussed yesterday, right? If you have H star, if you use the exact distance as your heuristic, then you will possibly not do any exploration. You'll be able to go to the goal state, right? At each step, you're going to the optimal state directly because you know H star. So G plus H star is that's the distance you actually care about, and you will get it. I mean, you will get the optimal path in one go. So, I think you can guess where I'm getting to. So all of these will guarantee optimality in the tree search case. But, at this end, you have like heavy exploration. At the bottom of this graph, you have this heavy exploration case. This heuristic leads to heavy exploration. And here you have almost zero exploration. And you like to get to H star, that's what you want, but since that's very hard to get H star, you have to choose some heuristics. So as you are closer and closer to the exact heuristic, to the exact distance value, your heuristic gets better and better in the sense that you're going to be optimal, but still you don't do too much exploration. So that's what you should aim for. Okay, when you design your heuristic, like you won't know the exact value, but in between these two, right, like for the case of the 8 puzzle problem, there was the tiles heuristic. So how many tiles are misplaced, that is a very small value. So it's at max in this case 8, right? Because there are 8 tiles and at max all 8 are misplaced, and that is the value. But actually the Manhattan heuristic was better here, okay, because that gave a sense of how much you're moving in order to get to the goal. At least you have to move that much. You might end up moving more, but so in that sense the Manhattan heuristic was a larger value than the number of tiles misplaced, and so that's why it did better. It was closer to the exact distance. Okay, so this kind of a structure you can draw for these admissible heuristics. So does this remind you of anything you have seen in any other course? This kind of diagram that I've drawn here. Are you all there?
I haven't seen the diagram.
You haven't seen this? Okay. So have you all done a course on discrete maths, discrete structures?
Yes, ma'am. Yeah, ma'am.
All right. So I don't know if you learned this, the notion of these partially ordered sets. Do you remember seeing something like that?
No, ma'am.
You didn't see that? Okay. So actually what happens is, let me just tell you very briefly about this. So the structure defines what is called, this partially ordered sets. So partially ordered set is basically a set of elements, partially ordered sets, or it's also called posets. Okay, so in discrete maths, what you have is you have these sets of elements, right? And there can be relations. So you know about relations and all, I hope. You've learned about relations in discrete maths?
Yes, ma'am.
Yes. So you know of these properties, right? Like reflexive, antisymmetric, transitive.
Yes, ma'am.
Yes.
Yes, those you have learned. Right. So okay, so a partially ordered set is just a collection of elements, and there is also a relation which is defined for this set. So in this case, the relation is this greater than or equal to relation, and we say that all these elements. I mean, you needn't have this relation between every element of this set, but whenever you have this relation, what it means is that this relation is reflexive, um, it is anti-symmetric, and it's also transitive. Anti-symmetric and transitive. So this is what defines a partially, it's a poset. So whenever this relation is defined, that relation may not exist between every pair of elements. If it exists between every pair of elements, we say it's a partial order. Okay, but all that it needs to satisfy for a poset is that the relation is reflexive, anti-symmetric, and transitive. So reflexive means that between you have a relation between the same two elements. So here you have that HA is actually related to itself, right? Because it is greater than or equal to itself for every state. Right, so that is true. And anti-symmetric, you have that either you have HA is greater than HC, or HC is greater than or equal to HA at only one of them. And if both happen, it should be that both are the same, right? So that is anti-symmetric. And transitive, so if HA has a relation with HC and HC has a relation with HB, then HA will also have a relation with HB. Right, so that's what it is. So these are some of the properties that this family of admissible heuristics has. Okay, so this is, sometimes it's nice to know this because these are some mathematical properties, and maybe there's something there which helps you further. But at the outset, one thing that you should keep in mind while designing heuristics is that it should be as close as possible to the exact value. Okay. So that's about the design. So you will also see this, or you might have already seen this in your lab exercise. So there's some parts where you have to design heuristics, and there you also have to design consistent heuristics. Okay, so yeah, you will have multiple options, but you have to choose something which is preferably as close as possible to the exact, and also which is consistent. Okay, so that's just some guidelines about how you make a choice of the heuristic. All right, so I think this was the last topic for informed search. So I'm going to start the next topic right away. But before that, I just want to ask, are there any questions? Any concerns, something unclear? Okay, can you just type? Nobody's speaking. Is it clear? It's not clear? Everything okay so far? Okay. Okay, maybe, yeah. I just want to see who all are there. So, okay. Okay, fine. So a lot of you were comfortable. All right. So can I also hear from some others, somebody who has not spoken much, maybe? I don't know. Who else is here? Like, okay, Karthik, I didn't hear from you, so
Yes, ma'am, it's clear.
things are fine. All right. Okay, so you have to be interactive, okay, all of you, and you have to stop me if there are any questions or, just be very active in class. Okay, because it's an online session, so it's more interesting for me also if people speak up. Okay. All right. So, okay. So with this, let me maybe move to the next topic. So this is, we are going to add one more level of complexity to the problem. Okay, just give me a second. Okay. So what we are now going to look at is the problem of multiple agents. So far when we looked at search, we were looking at the case where there's just one agent and it's kind of like a navigation problem where has to get to some place or do something to get from a start state to a goal state. Okay. There was no external agents or nothing of that sort. There were no dynamics from there. But today what we are going to do is we are going to introduce more agents and we're going to make it more exciting. So this is, you are also seeing this in Pac-Man, right? So you have these other ghosts which are coming and they're out to kill you. Okay, so then how do you take care of this situation? Because not only do you have to go around the board and eat all the dots, but you also have to protect yourself from being killed, right? So now there is something with the ghosts are moving around with some intention, and how do you make decisions here? Okay, so this is something, it is more closer to a lot of situations that happen, right? Even in real life, right? There'll be like, if you're working in some companies, there'll be companies like trying to compete against each other, right? And they'll have like similar products, they'll have some strategies that they take, and they everybody's is competing so that they survive. Okay, so that kind of a thing happens. I mean, it's not just in games, in reality also it happens. And another example is in driving, like people are going to do there's this notion called defensive driving, right? So where you assume that the other person is driving, I mean, he will hit you, he's coming to hit you, so you have to protect yourself. Okay, so that kind of thing happens. And also it's not just about this kind of competing nature. You also have cases where people are behaving randomly as well, and there is some model that you have, and you have to make a plan taking into consideration the other agents. So how do you do that? So that's going to be the next topic. And here you will have different models in which agents behave. So we will first start off with adversarial search. So this is the first type of multi-agent problem, adversarial search, where in this case people are competing against you. Okay, and you have to win. Either you win or you lose. So one person's win is the other person's loss, right? So that's what is the adversarial search setting. Okay. So maybe let me just get started about you. I think you understand the setting well because you've seen Pac-Man and you've seen how all these games are. Okay, so let me just get started about formally telling you what are the components now. Okay, so some components are basically what you have seen already in the first part in the search problem. So you have a set of states. Okay, so the components were, what all did you have there? You had states. What else did you have?
Actions.
You had actions. Yes. Then what else was there?
Successor function.
Successor functions, right? So we will call this, in this notion, we'll call this as a transition function. It's basically the same idea. If you have a state and an action, where you go to. Okay. Now another thing here is we have this notion of players also, right? So earlier there was just one player, but here you have like multiple players. So this player list is maybe something like this, 1 to n. There are n players. Okay. And at each, what happens is that in each round, so there is a first round in which agent 1 plays. Agent 1 decides to take an action, and then you go to some state in the in the whole space. There is a new state you go to, and then in round 2 the next agent comes. He observes the state, the new state, and then he takes an action. And so this is now a new state comes in. So this is state 2. So okay, maybe let me just write it a little properly. So what you have is a start state. Okay, so that's where you begin. Then there is, agent 1 plays something, takes an action, and then you go to a new state. So maybe you go to state 1, and then next agent 2 comes in. He sees that he's now in state 1, and agent 2 comes in, and then you go to a new state, state 2, like that. It goes on. And finally, you have agent N coming in. And so then you get a new state. So state N, and after this again it's the turn of agent 1. Okay, and this process goes on till you hit some end, right? So the game ends at some point. So that is called the point at which the game ends. That is called a terminal state. The state, the last state, after these multiple set of sequences, at some point we'll get what is called a terminal state. So that is also going to be a part of the search problem. So you have these states, you have the players playing this, actions, the various actions, and there's a transition function. Then there's going to be terminal states. So here what we will have is something called a terminal test function. Okay. So what this will tell you is for each state you give, it will give a true or false. Right? It's just going to tell you whether it's a terminal state or no. Okay. And the transition function is anyway the same. You have a set of states and actions, and they give rise to a new state. Okay. And you have the terminal test. And in addition, there's one more quantity here, which is called the terminal utilities. Okay. So for each state, each terminal state, right? So that is the sort of the game end state. There is a score that each of these agents get. So let me call this set P. So P is the set of players. So the terminal utilities is a mapping from each state. So this has to be a terminal state times the player. So for each player, there is a different reward for being in that end state. Okay, so this it takes a state and a player and gives some reward. Okay, so this is a real number. Okay. Yeah. Okay. So you can think of these utilities as like your final score, right? Or if it's the case of real problems, it could be something like a profit for being in that state, for ending at that state. Okay, profit or loss or whatever. So the idea is, usually you model it as a profit because you want these, the term utilities, it comes in, right? So it's like the benefit for each agent. And that is something that, each agent is trying to maximize. Okay. And so all these agents are rational. So they choose their actions in such a way so that, finally the game ends in a point where their utilities are maximized. Okay. So I hope this setting is clear. Are there any questions on this setting? Okay, so you should be able to map this on to Pac-Man and identify what these, for all those examples that you have in the labs, right? The set of problems, you should be able to figure out what a terminal utility is, what a terminal test would do. Okay, so that would come in the next set of assignments. Okay, but this is something like you should think of. Like for each game, try to see what happens here. Any game you take where there are multiple players, try to construct these states, action, the transition function, and all these components. Okay. So what we will do now is we will go into the case of two-player games. So typically you can have like multiple agents. The agents are like, from 1 to n, and you have this cyclic kind of, each player has his turn. So for simplicity, we will just start off with two-player games. And then this will extend. I mean, you can extend it to multiplayers. And in fact, your programming assignment is going to do that. But let's start off with two-player games. Okay. Now, in the context of these adversarial games, these are also called zero-sum games. Okay. So, okay, maybe let me just ask you guys, what will you do in Pac-Man, right? When you are playing this game? Okay, all the agents have died. Okay. So let me ask you, what would you do here? So there's this agent which is going around, right? The yellow guy, and there are the ghosts, right? So you know that the ghosts are out to kill you, right? So what is a strategy you would do? Like, how would you move around? Can somebody tell? All of you are Pac-Man experts now, right? I think you already were. Hopefully you are getting better and better at Pac-Man. So what is a strategy you would use?
We'll probably get away from the ghosts, and if there is a power palette and the Pac-Man agent already is at the power palette, then we try to get towards the ghosts.
Towards the ghost, exactly, right? So the case where there's a power pellet and the ghost becomes like your friend. It's now the ghost is no longer your adversary at that stage, right? But until then, when you don't have the power pellet, you're only trying to get away from the ghost, right? Now, would you always try to get away, or if there are some food particles like near you, and the ghost is very far, so what would you do then?
I'm not exactly get away. Like if there are chances to eat the food near the ghost, then definitely the Pac-Man will eat that food and get away from the ghost.
Yeah, so exactly, right? So you eat as fast as possible. Yes, that's true. So what you do is you make a calculation, right? You get a sense of, is the ghost going to come towards you? And in that time, how much can you finish, and how can you also stay away from the ghost? These are some decisions that you make. Now, when you play the game, this is exactly what's going on. I mean, though you don't explicitly think of all these, but in some sense, this is what is going on, right? You try to finish up the dots as quickly as possible before the ghost comes, and you are seeing the ghost, you know where the ghost is, and then you are able to make a judgment of whether the ghost will come towards you. So even that's exactly what, when you automate the agent, you want the agent to do. Okay, but not in the sense of explicitly giving these instructions, but the agent has to, get an idea of it on its own, or not fully on its own, with minimal inputs from your side. Okay, so let's just see what exactly is happening. So these zero-sum games are exactly this thing. So when you have, so let me say like there are two agents now. So there's Pac-Man and then there's a ghost. So let's say Pac-Man and then there is a ghost. So there's just one ghost, okay? And so if Pac-Man is going to win, ghost is going to lose, right? So suppose, Pac-Man's utility is something like 100 at a terminal state. When the game ends, if Pac-Man gets 100, it's as if the ghost is going to have minus 100, right? So, and similarly, if you get eaten by a ghost, the ghost wins. So ghost is going to have 100 and Pac-Man is going to have minus 100. So this is a case when this is a win for Pac-Man and this is like a lose. Okay, so that's why, these are called zero-sum games, because, these utilities, if you take, it's the equal utility for the other agent. One agent has some utility at a terminal state. The other agent has the exact equal and opposite utility. Okay, it's like a opposite reaction kind of a thing. Okay, so that's why these are called zero-sum games. Okay, so let me just maybe also explain the concept of adversarial search trees or adversarial game trees now. So this is actually quite similar to what you saw in the first part, like where we saw search trees. So the concept is almost the same. It's just that you have now two players. So let me just take an example. Okay, yeah. Before I do this, maybe I should also say one thing. So yeah, you see these zero sum games, right? So one is 100 and the other one is going to be minus 100. So when Pac-Man is going to choose an action, it's going to try and maximize this utility, right? And so when the ghost plays, it's going to try to minimize this utility. It's going to try to maximize its utility, but that is going to end up hurting you. Okay, so in that sense, its ghost is trying to minimize your utility, and you have to try to maximize your utility. So there is this max and min kind of a situation which is coming in. So because these utilities of both these agents are the same, but just the signs are different. Usually, you only use one of the numbers. So typically, what you will model is your utility, right, or Pac-Man's utility. So the agent for whom you are trying to mimic, or the agent for whom you are serving to proxy, that agent's utility is the only thing that you will represent. Okay, and then everything else is in terms of either maximizing that utility or minimizing that utility. So the game tree will have these components, the utilities. So how it works is it's exactly like you expand all the possibilities that happen. So suppose you are initially in the start state, okay, and now it's the turn for Pac-Man, suppose. So Pac-Man plays something. So this is the turn of Pac-Man. And this agent, will also call him as a max agent because you want to maximize the utilities for this agent. Okay, so Pac-Man is going to play some action. So there are some possible actions. Okay, so let me just take two actions for the time being. And then, so he has played this action, and then there is a state, this new state that you have landed up in. So I'll just call it A and B. So A and B. Now in this state, what is going to happen is it's now the turn of the ghost to play. Okay, so this is the turn of the ghost. And the ghost is, we will refer to this as the min agent. So it's the agent who is trying to hurt you. It's trying to hurt you because his or her utilities get maximized when your utility is less, right? So when you lose, so if you get minus 100, the ghost is going to get 100. So in that sense, he's trying to hurt you. So that's why it's the min agent. And now the min agent will play. Okay, so there'll be some other set of actions, and this will go on. So next turn will again be the max agent. I intended to use different color codes here. So this is like the min agent. Okay, and
Can you explain min agents and max agents again?
Yeah, so you get this idea of these equal and opposite utilities, right? Is that
Yes,
idea
ma'am.
clear? That's clear.
Yes, ma'am.
So, right. So the ghost, this is the utility of the ghost, this minus 100 and 100 at these states. So if the ghost is trying to play, it is trying to maximize its utility. So that would be, it is trying to get here to this part, right? So this one. But
Yes,
what that would do is it's actually promoting a low utility for you, right? So in that sense, the ghost is trying to minimize your utility.
yes, ma'am.
Right?
But ma'am, like here, how ghost is going from minus 100 to plus 100?
Yeah,
In
that
what
we will
sense?
see. Okay, these are some configurations I just told. So this can be one state where these are the utilities. This is another state where these are the utilities. Okay, these are two different states.
Okay.
But what I'm trying, right? But when what I'm trying to say is when the ghost starts, he's trying to get to this state, the loose state actually for you. Okay, so in that sense, it's trying to hurt you, and so we call it a min agent. So finally, what is going to happen is, we will not use these numbers. We will represent everything in terms of Pac-Man's utilities. And so the ghost is trying to minimize the utility for Pac-Man. Okay, so
Okay.
that's right. So that's why it's a min agent. And so what happens is this game continues like this, right? So several rounds of the game happen. So the next, again at this point, you have the max agent coming in, and alternatively they go max min, like that it goes, and finally you have some terminal states. Okay, so there are some terminal states here, and each of them will have some utilities. Okay, so we will we'll write some numbers here. So those will be the utilities for Pac-Man or the max agent. So these are the utilities that the max agent gets. So it could be something like 100, maybe 8, maybe when this is a losing state. So it will be maybe a -5, maybe a -100, something like that. So these are the various possibilities. So if Pac-Man starts off with A1 action and the ghost plays this action, and so on. If this is the trajectory that it's followed, finally it lands up at a win for Pac-Man. Okay, and whereas if it followed some other trajectory, it would lead to a loss for Pac-Man. Okay, so that is -100, but this is actually a win for the ghost. But anyway, we will see it, all these numbers refer to the utilities for. So these are utilities for the max agent. Okay, so so this is going to be the framework, and what you need to do, what Pac-Man or the ghost, what they have to do is at each stage they will have to come up with what is the best action for them, right? So in some sense, you are trying to like if you knew this tree, you try to build backwards and backwards, right? So you so you start off with 100, and then you try to propagate something up, and you try to calculate in advance, so which action will get you to 100, right? So that's exactly what we will do here. And so these kind of agents are also called mini-max agents. Okay, so I don't know why it's called mini-max. It has to be max-min, right? Because agent is trying to maximize in the presence of a min agent. But anyway, these are called mini-max agents. Okay, so let me just take a concrete example for this to illustrate. So let's start off with this. So we have the first player here, who's a max agent, and there are two actions, A1, A2, and then there are these second state. So this is S2 and S3. So these are states for the min, where the min agent is going to come in. And again, maybe B1, B2, B3. Okay, so let it be like this. And so these values that are, so suppose they're just two plays. So first agent 1 plays, and then the second agent plays, and finally the game ends. Okay, so at the end, maybe these are the utilities, -8, something like this, 2, 1, -3. Okay, now let me just make one of these +5. Yeah. Okay, so suppose this is the case, and the agent 1 is going to start. Okay, so we also define what is called a value of a state. So typically the terminal states have some utilities. Now we'll define what is called value of every state. So what it means is, what is the best achievable utility at that state? I mean, for that agent which controls. So what I mean is, in this state, the first agent is controlling, but in these two states, the second agent is controlling. Now, if you just look at S2, state S2, there are three possibilities for the min agent. So it's B1, B2, B3. And these are going to give -8, -5, and 5 for the player 1. Okay, so this agent, the second agent, is going to try to minimize these numbers. He's going to play an action such that the terminal utility is as low as possible, right? So what is the lowest here of these three numbers?
-8.
-8, right? So that is the value of this state S2, right? Because he's trying to play in a way to make things as good as possible for him. And in the process, he's going to choose the minimum utility, right? And what about S3? In the same way, what is the, what is this? This is also -3, right? Okay, so that is the value of these states. So the value is in, what it means is the best achievable, best achievable utility at that state for that state. Okay, so it also depends on who is controlling it. So, but the value of the utility we will always write in terms of the max players. Okay. Okay, now what about this state? So this is, let me call this S1. So at S1, when from the point of view of the max player, he knows that the min player will choose something which gives him -8 if he was at S2, and he would choose something which gave -3 if he was at S3. Okay, so when player 1 looks at it, these are the utilities that he will get. Okay, when the turn goes to the next guy. So what is going to be the value of this? So here you have to do a max, right? So the best achievable is the max of these numbers for him. So what's the max utility?
-3.
-3, right? So this is the value of this state for the first player. So what he's going to do is now he will play this action A2, which corresponds to giving him the max utility, max value. Okay, because if he plays A2, then the second player comes in and will play something to hurt him. So he will choose this action, B3, right? But whereas if he played A1, then the second player will come in and he will choose B1, right? Which will hurt him even more. Okay, so that's how this game is going to work. And so the best action here is A2. Okay, so this is the correct one. Okay, so I hope this procedure is kind of clear to you all. Right. Are there any questions?
Ma'am, let's say, can you switch the tab back to the, let's say S1 follows path S2 and he achieves like a utility greater than if he follows S3 path.
So if he follows,
let's say if the Pac-Man follows S2 path, S2 state,
okay,
then
comes here.
Then in future it will achieve the greater utility as compared to S3.
So he will. Are you saying that this can happen? This B3 action as the age. So these states are under the control of the second player, of the ghost.
Yes, ma'am.
Right. So your point is that if the ghost plays B3, then he will get a greater utility. Is that what you're saying?
Let's say if we change -8 to -3 and -3 to -8.
Okay, so this instead of this you have -3.
And yes,
okay.
and instead of this, and we have -8.
Mm-hmm.
So if we follow S3, we will reach at point -8.
Yeah, that's true. Yeah. So
overall, if we see like it will like S2 state will be more benefited as if we look at if we like the overall state. You're understanding what I'm saying?
So you're saying like if the utility changes, then you're in trouble. Is that what you're saying?
Yes, ma'am.
Yeah, that is right. So if the game was instead -3 if this was the set of utilities, then the player should have gone for this action A1, because in the worst case, the player 2 is going to choose something to hurt you. So yeah, you're right. So if the utilities were different, this is what is going to happen. But here the assumption is that the other agent is also rational, and these utilities are known to you. There's nothing that's going to change about this. So this is not a random quantity now. Okay, this suppose you already know. Somebody told you that in this state, this is going to be the set of utilities that you will get. That is a fixed quantity, right? Like in Pac-Man, at the final state, there'll be some configuration, right, of all the dots and the positions of the ghosts and everything. So considering all that, there is one value for that state.
Yes, ma'am.
Right? So that is not going to change. For the same state, you will not have different possible utilities.
Okay.
Yeah, but I see your question. So you have to do something else if these utilities are going to change, and if you don't know the utilities in advance, right?
Like
so
here we greedily choose like whatever best for a local maximum. Like we achieve local maxima for our current state. But in future, if there is a maximum to another state, then what we gonna do? Like we reached at -8 if we follow S3 state.
Mm-hmm.
After selecting S3 because it is -3 and it is maximum of -8 and -3. But the overall benefit for us is reaching -3 from S2 state.
So you're saying for the ones in black for this set of utilities?
Yes, ma'am.
Yeah. So the overall benefit, yes. You are anticipating that the second player will behave in the worst possible way, and then you will choose an action, right? But these numbers are, there's no change here. This is given to you. This will there's no way that this will change. Right?
And like first player chooses a worst case. First player choose S2 state, that is -8.
Yes.
And after that, ghost chooses state which is worst here. That is -5. B2.
But there is no incentive for the ghost to choose B2 because the ghost is also a rational agent. Okay, you're telling for this one. Okay, I'm getting confused whether you're talking of -8 or -5. So let's fix this one, right?
Yes, ma'am. Yes.
Okay, yeah. So here the ghost is going to choose B2. Yes. So that the final utility is -5 for Pac-Man. Yes.
For Pac-Man. But
yes.
Ma'am, if we follow your approach, like the Pac-Man chooses best state, and if that's gonna case, then the Pac-Man chooses S3 state, and it will comes up, and in the end, we will get to the state of -8.
Yeah, that's true. So if these were the utilities, then you'll have to rework this. The strategy will be different, right?
Okay.
So if this was the set of utilities, what is going to happen here? The value, I'm just writing in different color, okay, so that to be clear. So the value of S3 would be min of these. So that would give you -8.
Yes.
Right. And the value of S2 would be the min. So that would be what?
-5.
-5, right? And now for when it comes to S1, the choice is between -5 and -8. So the max of this is what? -5.
Yes, ma'am.
Right. So at this state, you will take the max of the, for the actions below, the max of these value of the states below. So here you are again going to get -5, and the action should be A1.
Okay.
Okay.
Got it.
So if your terminal utilities are a different set of value, you'll have to again work this out and find the best set of actions. Okay, so this best strategy is for a fixed configuration of the terminal utilities, you will have what is the best. Okay, so I hope this is clear to you. So who was asking? Sahil, right? Sahil.
Yes, ma'am.
Okay. Okay, so I think we are running short of time, so maybe I will end it here. I wanted to give the algorithm, but maybe I will start the next class with the formal algorithm to compute this. Okay, so we will end here, and so just a reminder again. So for today, you have a lab session at 4 p.m. So all of you, please show up. Okay. So yeah, if there are no questions, I'll end here. I'll just hang back here for some time in case there is anything else. So thanks everyone.